There's a funny thing about stars that almost nobody notices at first, because once you notice it, it feels so obvious that you can't believe you didn't see it before. Tonight, if you can step outside, look up the sky. Don't worry about constellations or names or any of that business. Just stare at one bright star. Pick one. Fix your eyes on it. Now here's the strange thing. It twinkles. It sparkles. It flickers. It seems alive, like a tiny diamond shaking in the dark. But here's the paradox that always tickles me: that star is not doing anything at all. It's not flickering. It's not dancing. In fact, it's doing the most boring thing you can imagine. It's just steadily shining, calmly, smoothly, constantly, like a gigantic, unimaginably steady light bulb. So why on earth, literally on earth, does it look like it's wiggling and blinking and jittering around like it's nervous? And here's where the story gets even stranger. If you were sitting on the moon, that same star wouldn't twinkle at all, perfectly steady, like a pin stuck into black velvet, no sparkle, no flicker, no magic. Which means, and this is the delightful twist, the twinkling is not happening out there in the universe. It's happening right here, inside the thin shell of air wrapped around our planet. The thing you're seeing isn't really a property of the star at all. It's an illusion. An optical illusion created by Earth's atmosphere, by the very air you breathe. And that's already kind of wonderful, because it flips the usual way we think. We imagine we're looking outward into space, observing the universe as it truly is. But most of the time, what we're really seeing is the universe after it's been scrambled, bent, shaken, and distorted by our own environment. It's like trying to look at someone clearly while you're peering through the wavy glass of an old shower door. The person isn't wiggling, you are looking through something that's wobbling. And that idea that what we see isn't always out there, but often something happening in between, that's one of the deepest lessons in physics, because nature loves to play this trick on us. It makes us think we're seeing things directly, when really we're seeing the effects of the medium through which the information travels. Let me put it to you this way. Imagine you're sitting at the bottom of a swimming pool, looking up at a bright light above the surface. The water is gently rippling. What happens to the light? It dances, it stretches and contracts. It seems to shimmer and swirl and jitter around, but the light source itself hasn't changed one bit. All that motion, the entire show, is created by the moving water between you and the light. Now here's the thing that's so charming: the air above your head behaves like that rippling water all the time. We just don't notice it. We think of air as empty, still, transparent. But it's not. It's boiling. Not hot boiling, of course, but it's constantly churning with little currents of warm and cool air mixing together. Tiny invisible pockets of different temperatures, different densities, sliding and swirling around one another. And each of those little pockets bends light just a tiny bit. Just a tiny bit. But when starlight travels for trillions of kilometers across empty space, perfectly straight, perfectly steady, and then enters this thin, restless ocean of air in the last fraction of a second before reaching your eye, it gets tossed around, jiggled, refracted again and again. So by the time it hits your retina, it looks like the star is dancing. But it isn't. And this is where I always get a little amused, because it means something very profound. The universe, most of the time, is much calmer than it appears to us. The drama, the flickering, the shimmering, the apparent chaos is often coming from us, from our viewpoint, from the tiny local conditions around our little planet. It's like listening to a perfectly steady radio signal while driving through a tunnel. The signal doesn't change, but your reception does. Static appears. The sound crackles. It fades in and out. And you might be tempted to think the broadcast itself is unstable. But really, it's just the environment between you and the source. Now, if you sit with that idea for a moment, it becomes even more delicious, because it raises a very unsettling question. How many things in life, not just stars, appear to flicker, change, or wobble, not because they actually do, but because of the medium through which we perceive them? How much of reality is steady, and how much of what we experience is distortion? And that's where things start to get really fun, because once you understand why stars twinkle, you begin to realize that the atmosphere isn't just horn the way. It's actually performing a constant experiment for you, an experiment about light, motion, temperature, and the nature of perception itself. And if you look closely enough at that tiny flicker of a distant star, you can actually see the invisible motion of the air above you. You can see the restless activity of the planet you're standing on. You can see the physics of turbulence playing out in real time. You can even start to understand why planets don't twinkle the same way stars do, which is a mystery that surprises almost everyone the first time they notice it. And once you start asking that question, well, that's when the real adventure begins. Because to understand why stars twinkle and why that twinkling is, in a very real sense, an illusion, you have to take a little journey into how light travels, how air behaves, and how unbelievably sensitive your eyes are to tiny changes in direction. And along the way, you discover something quite astonishing. The night sky isn't just showing you the universe, it's also showing you the invisible physics happening right above your head. And that is a story worth exploring. Alright, so let's play a little game of imagination together, because physics is really just imagination that happens to be correct. Suppose you had a magical elevator, one that could quietly lift you straight up into the sky. No wind rushing, no noise, just a smooth ride upward. You start at the ground. You're looking at a bright star, twinkling, dancing. Now the elevator rises a few hundred meters, still twinkling. Up it goes 1 kilometer, 2 kilometers, 5 kilometers. And something very interesting begins to happen. The twinkling gets weaker, not gone yet, but softer, less frantic. You go higher, 10 kilometers, 20, 30. Now the star looks calmer, and eventually, if you ride that elevator high enough, right past the atmosphere entirely, the twinkling disappears completely. The star becomes perfectly steady, like a tiny laser dot frozen in the darkness. And that thought experiment alone tells you something extremely powerful. It tells you the flicker isn't in the star. It isn't in space. It's happening in that thin, restless layer of air wrapped around Earth. Now here's where things get really interesting. You might think of air as just air. Nothing special. Just a clear, empty substance. But air is actually one of the most complicated, lively, chaotic things you can imagine. It's constantly moving. Warm air rises. Cool air sinks. Wind shears slide layers across each other. Little swirls form and break apart endlessly. It's like an invisible ocean. And just like the ocean has waves of different sizes, from tiny ripples to giant rolling swells, the atmosphere has waves of density. Some pockets of air are slightly warmer, slightly thinner. Others are cooler, slightly denser. And here's the key idea. Light bends when it moves from one density to another. This bending is called refraction. You've seen it 1,000 times without thinking about it. Stick a spoon in a glass of water, and it looks bent. That's not because the spoon is bent. It's because light changes direction when it moves between materials of different densities. Now imagine something far more delicate. Imagine light traveling across the vast emptiness of space for millions of years, perfectly straight, never touching anything. Then, in the last few milliseconds of its journey, it plunges into Earth's atmosphere, a chaotic, shifting maze of tiny density changes. Every little pocket bends the light just a bit, left, right, up, down, just a tiny amount each time. And because the air is moving, those pockets are constantly shifting. So the path of the light is constantly changing, which means the exact point where the light lands on your retina is constantly shifting too. And that tiny wandering of the light point, that's what your brain interprets as twinkling. The star isn't flickering. The light from the star is being wiggled. It's like trying to shine a laser pointer through rising heat waves above a road on a hot day. The beam seems to dance around, not because the laser is unstable, but because the air itself is bending the path. And here's a delightful little experiment you can try. Look at a star near the horizon. Notice how wildly it twinkles. Now look at a star directly overhead, much calmer. Why? Because when you look toward the horizon, the starlight has to travel through a much thicker slice of atmosphere, a longer path through the wavy glass. More turbulence means more distortion. Straight overhead, the light passes through a thinner layer, less chance to get scrambled, so the twinkling weakens. And that's one of those moments in physics that feels almost poetic, because it means that when you watch a star flicker, you're actually seeing the invisible weather of the sky. You're watching turbulence. You're watching temperature differences. You're watching the restless motion of the atmosphere. The air becomes visible, not directly, but through its effect on light. Now here's something even more surprising. Planets don't twinkle nearly as much. Have you ever noticed that? Most people haven't until someone points it out. A planet like Jupiter or Venus usually shines with a steady glow, almost calm compared to stars, and that seems strange at first. After all, the light from a planet passes through the same atmosphere, doesn't it? So why doesn't it flicker the same way? The answer is one of those beautiful little pieces of reasoning that shows how physics connects things you'd never expect. It comes down to size, not actual size, but apparent size. A star is unbelievably far away, so far that, to your eye, it's essentially a point, not a disk, not an object with width, just a single infinitesimal dot. All of its light reaches your eye from almost exactly the same direction. So when atmospheric turbulence bends that direction slightly, the entire point shifts. That creates dramatic flickering. But a planet, even though it's far away, is much closer than a star, close enough that it appears as a tiny disk, not a point. Light from one edge of that disk travels through slightly different paths in the atmosphere than light from the other edge. So when turbulence bends one part of the light one way, another part bends slightly differently. And all those tiny shifts average out, the result, a steady glow instead of a sharp flicker. It's like comparing a laser pointer to a flashlight shining through rippling water. The laser dot dances wildly. The flashlight beam looks steady. Because the flashlight is width, it averages over many paths. And that little insight reveals something profound about perception. Whether something appears stable or unstable depends not only on the object itself, but on the scale at which you observe it. Tiny points are sensitive to disturbance. Larger objects average out chaos. And this idea pops up everywhere in physics, in noise, in measurement, in statistics, in thermodynamics, even in everyday life. The smaller and more precise you try to measure something, the more jitter you see. Zoom in enough and everything looks turbulent. Zoom out and things become smooth again. Now there's another layer to this story that I always find delightful. Because when astronomers build telescopes, they face an incredible challenge. You'd think the biggest problem in observing distant stars would be the enormous distance itself. But no, the biggest obstacle is our own atmosphere. It's the wobbling air above us that blurs images. Even the most powerful telescope on Earth can't achieve its full clarity because the atmosphere smears the incoming light. It's like trying to read fine print through the bottom of a swimming pool. So astronomers developed something truly ingenious. They invented something called adaptive optics. Imagine a telescope with a mirror that can change shape hundreds of times per second. It constantly measures how incoming starlight is being distorted by the atmosphere, and then bends its mirror in the opposite way to cancel the distortion. It's like creating an equal and opposite ripple to flatten the waves. And when they do this, something astonishing happens. The blurry twinkling star snaps into sharp focus. It becomes calm, precise, stable, exactly as it truly is in space. And I love this because it's a perfect metaphor for science itself. Nature sends us signals. Those signals get distorted by our limitations, our environment, our imperfect perception. And the job of science is to build adaptive optics for the mind, to correct for distortions so we can see reality more clearly. But now, if we dig just a little deeper, something truly mind-bending appears. Because the twinkling of stars isn't just a simple bending of light. It's connected to one of the most complicated phenomena in all of physics, turbulence. And turbulence is so complex that even today, despite all our equations and computers, we still don't fully understand it. In fact, if you could solve turbulence perfectly, you'd probably become one of the most famous physicists in history. Because turbulence is chaos in motion. Swirls inside swirls inside swirls. Energy cascading from large eddies down to tiny ones. Endless, unpredictable motion. And every time you look up at a twinkling star, you are literally seeing turbulence at work. You're seeing the chaotic structure of air currents mapped onto a beam of light. The sky becomes a giant screen displaying the invisible physics of fluid motion. Which means something rather poetic. That tiny flicker from a star billions of kilometers away is telling you something about the air just a few kilometers above your head, the farthest and the nearest connected by a single beam of light. And that connection, that delicate interplay between cosmic distance and local chaos, is where the story starts to open into something even deeper. Because once you understand that stars don't actually twinkle, that the flicker is an illusion created by the medium between you and reality, you begin to realize that this idea doesn't just apply to stars. It applies to almost everything we perceive. And that's where the journey takes a fascinating turn. Because the next question isn't just, why do stars twinkle? The next question is, how much of what we think we see in the universe is shaped, not by the universe itself, but by the filters through which we observe it? And that question leads us into some very surprising territory. Now here's where things begin to get a little more subtle, and also a lot more beautiful. Because up to now we've been talking about twinkling as if it's just random wobbling, like a shaky reflection in water. But it's not merely random. There's structure hidden inside that chaos. In fact, if you had extremely sensitive instruments, and physicists do, you could actually study the twinkling of stars to learn detailed information about the atmosphere itself. Think about that for a moment. A star may be hundreds of trillions of kilometers away, yet the tiny flicker of its light in the last few milliseconds before it reaches your eye carries information about the invisible motions of air just above Earth. It's like a message that traveled across the universe only to whisper secrets about your own planet. And to understand how that works, we need to talk about something that sounds simple but turns out to be wonderfully strange. What does it actually mean for light to travel in a straight line? Because you've probably heard that phrase since childhood, light travels in straight lines. But the moment light enters something like air, the story becomes far more interesting. You see, air isn't uniform. It's not the same everywhere. It has tiny variations in temperature, pressure, and density. And each of those variations slightly changes something called the refractive index, which is just a fancy way of saying how much light slows down and bends when passing through a material. Now imagine light entering a region where the refractive index changes continuously, like a gradient. The light doesn't just bend once, it curves smoothly, it gets gently steered, and when you have many layers of constantly shifting air, each with slightly different refractive properties, the path of the light becomes a constantly changing, wiggly trajectory. It's not straight anymore, it's wandering, not wildly, but just enough that when it finally arrives at your eye, its direction has jittered slightly. And here's the subtle part that's really fascinating. Your eye is incredibly sensitive to direction. A tiny change in the angle of incoming light, even a fraction of a degree, can shift the apparent position of a star on your retina. And because a star is effectively a point source, that tiny angular change makes it appear to jump around in brightness and position. But here's something deeper. The twinkling isn't just a change in position. It's also a change in brightness. Sometimes a star looks brighter, sometimes dimmer moment by moment, and this happens because of something called scintillation. That's the scientific term for twinkling. And scintillation happens because turbulence doesn't just bend light, it also focuses and defocuses it. Imagine shining a flashlight through the bottom of a swimming pool on a sunny day. You'll see bright patches and dark patches dancing on the pool floor. Those bright patches happen where the water waves momentarily focus the light like tiny lenses. The dark patches occur where the light spreads out. The atmosphere does exactly the same thing to starlight. Tiny pockets of air act like countless moving lenses. Some focus the light toward your eye, making the star momentarily brighter. Others scatter it slightly, making it dimmer. So the twinkling you see is actually a combination of two effects, tiny shifts in direction and tiny changes in intensity, and that means every flicker you see is really a dynamic map of the atmosphere's turbulence. Now here's where things get wonderfully counterintuitive. You might think turbulence is just random chaos, completely unpredictable. But in physics, even chaos has patterns. Turbulence follows certain statistical laws. Energy flows through it in a cascade, from large swirling motions down to smaller and smaller eddies. Big air currents break into smaller ones, which break into even smaller ones, all the way down to tiny scales where the motion finally dissipates into heat. And each scale of turbulence affects light in a slightly different way. Large atmospheric waves bend the light more slowly and smoothly. Tiny eddies cause rapid, jittery flickering. So if you could analyze the precise way a star twinkles, how fast, how intensely, how the brightness fluctuates, you could actually reconstruct information about the size and motion of atmospheric turbulence layers. It's like listening to a distorted radio signal and figuring out the shape of the hills between you and the transmitter. And this is exactly what astronomers sometimes do. They use stars as probes. They measure scintillation patterns to understand atmospheric conditions. Because the atmosphere, which seems invisible to us, leaves fingerprints on every beam of starlight. Now here comes one of my favorite twists in this story. The twinkling of stars is, in a sense, a failure of clarity. It's an obstacle to precise observation. Astronomers hate it. They build telescopes on mountaintops, in deserts, in Antarctica, anywhere the air is stable to reduce it. They launch telescopes into space specifically to escape it. But at the same time, the twinkling is also incredibly valuable, because without it we wouldn't easily perceive the atmosphere at all. The sky would appear perfectly still and empty. We wouldn't have this constant reminder that the air above us is alive with motion. So the twinkling is both a nuisance and a revelation. It blurs our view of the universe, yet reveals the dynamic nature of our own planet, and that duality, that something can both obscure and inform at the same time, is one of the most profound themes in physics. Measurement always involves interaction. Whenever you observe something, you are also observing the medium through which information travels. You can't completely separate the signal from the path it took to reach you. And this idea doesn't stop with starlight. It appears everywhere. When you listen to music through a wall, the wall shapes what you hear. When you look at a distant mountain through heat haze, the air reshapes its appearance. Even when you measure particles in quantum physics, the act of observation itself influences the outcome. Reality as we perceive it is never just the object alone. It's always the object plus the journey the information took to reach us. And the twinkling of stars is one of the most gentle, everyday demonstrations of that truth. Now here's something that really tickles the imagination. Think about the path of a single photon, the smallest unit of light from a distant star. That photon may have left the star millions of years ago. It traveled across empty space, perfectly undisturbed. It passed through interstellar dust, magnetic fields, cosmic radiation, all without noticeable deviation. Then, in the final milliseconds before reaching your eye, it enters Earth's atmosphere. And suddenly it gets tossed around by tiny pockets of air only meters wide. After an unimaginable journey of perfect straightness, its last tiny stretch becomes chaotic. It's like someone running flawlessly across an entire continent only to stumble on the final step of their doorstep. And yet, without that stumble, you wouldn't see the twinkle. Without that atmospheric disturbance, the night sky would look far more static, far less alive, and this leads us into something much deeper. Because the twinkling of stars is really teaching us something about perception itself. It shows us that what we see is not just a reflection of distant reality, it's also a reflection of local conditions, of the medium, of our own limitations. It tells us that the universe we experience is always a combination of truth and distortion. And once you begin to see that, you start to realize something quite extraordinary. The flickering star isn't just telling you about light or air or turbulence. It's quietly hinting at a much larger philosophical idea that clarity and understanding often requires recognizing and correcting for the distortions between us and reality. And when you think about it long enough, that idea stretches far beyond physics. It touches how we interpret data, how we understand people, how we make sense of the world. Because so often, what appears unstable, chaotic, or inconsistent isn't the thing itself. It's the medium through which we're perceiving it. And that realization, that moment when you recognize the difference between the signal and the distortion, that's when your understanding suddenly becomes much deeper. And that's where the story of twinkling stars begins to open into something even bigger than optics or atmospheric physics. Because it starts to connect with how we think about reality, time, and our place in the universe itself. And that is where things become truly astonishing. You know, if you sit long enough under a night sky, really sit, not just glance, you start to notice something very curious happening in your mind. At first, you see stars as objects, little points of light stuck on a black background. But after a while, once you understand what's really going on, the picture changes completely. You're no longer just looking at distant suns. You're looking at a story unfolding between them and you. A story that stretches across time, space, motion, and perception all at once. Because here's the thing that always makes me pause when I think about twinkling stars. The light you're seeing right now is ancient. Not metaphorically ancient, literally ancient. Some of it left its source before human civilization even existed. Some photons you see tonight may have started their journey before the pyramids were built, some before humans learned to write, some before humans even existed. And those photons traveled across unimaginable distances in perfect stillness. For millions or even billions of years, they moved in straight lines through the quiet vacuum of space. No air, no turbulence, no distortion, nothing to disturb them. And then after that perfect, pristine journey, in the last tiny fraction of a second before reaching your eye, they hit Earth's atmosphere, and suddenly they wobble, they flicker, they dance. It's such a wonderfully ironic situation. The longest part of the journey is perfectly calm. The shortest part is chaotic. It's like writing a flawless, beautiful letter over decades, only to have it crumpled slightly by the wind just before someone reads it. And yet, without that crumpling, you would never notice the wind. Without that flicker, you would never perceive the invisible air around you. So in a very real sense, every twinkling star is showing you two things at once. It's showing you the immense calm of the universal and the restless activity of your own tiny planet. The vast and the local superimposed, cosmic stillness filtered through earthly chaos. And when you realize that, something shifts in how you think about reality, because it becomes clear that what we perceive is never just what is, It's always what is after it passes through layers of interpretation, distortion, and limitation. Your eyes don't see the star directly. They see the star plus the atmosphere, plus the optical imperfections of your eye, plus the processing of your brain, plus the assumptions your mind makes about brightness and contrast. So what you experience is always a kind of collaboration between reality and the filters through which you encounter it. And this isn't just true for starlight. It's true for everything. When you hear a sound, you're not just hearing the source, you're hearing the room, the echoes, the medium of air. When you observe a scientific measurement, you're not just seeing the phenomenon, you're seeing the instrument's limitations, the noise, the environment. Even when you form an opinion about something, you're not perceiving it directly. You're perceiving it through the lens of your experiences, expectations, and biases. And the twinkling of stars becomes a quiet little reminder of this universal truth. Reality is never encountered raw. It always arrives filtered. But here's where it becomes really beautiful. Science doesn't just accept those distortions, it learns to understand them, to measure them, to correct for them. Think about astronomers again for a moment. They know the atmosphere distorts starlight. So what do? They study the distortion. They measure how the light wobbles. They build models of turbulence. They design adaptive mirrors that change shape hundreds of times per second to cancel the atmosphere's effects. And when they do that, something magical happens. The twinkling disappears. The star snaps into perfect clarity. And in that moment, you see something very profound about how knowledge works. Understanding doesn't come from ignoring distortions. It comes from recognizing them, from accounting for them, from separating the signal from the noise. And that process, that careful, patient disentangling, is really the essence of science itself. Now there's another layer to this story that I find almost poetic. Because the twinkling of stars is not just about distortion. It's also about connection. Think about it this way. That flicker you see in the sky is caused by tiny fluctuations in air density, differences in temperature and motion in the atmosphere. Those fluctuations are influenced by wind patterns, by sunlight heating the ground during the day, by weather systems moving across continents. Which means the twinkle of a star tonight is partly shaped by the weather of your planet, by the warmth of the land beneath you, by the motion of air currents overhead. In other words, the light from a distant star carries a tiny imprint of Earth's present moment. A photon that traveled for millions of years in silence becomes, in its final instant, shaped by the living, breathing dynamics of our world. So when you look up at a twinkling star, you are witnessing an interaction between two extremes of existence, the ancient and the immediate, the cosmic and the local, the eternal and the transient, and that realization can do something very curious to your sense of scale, because it reminds you that you're not just an observer standing apart from the universe. You're part of the chain of events that shapes what you see. Your atmosphere shapes the light. Your eyes detect it. Your brain interprets it. Your mind assigns meaning to it. You are not separate from the observation. You are part of the process. And this idea that the observer and the observed are linked through a chain of interactions is one of the deepest insights in all of physics. It shows up in optics, in thermodynamics, in quantum mechanics, everywhere. We never see reality directly. We see reality through relationships, through interactions, through the exchange of information. And the twinkling of stars is one of the most gentle, everyday demonstrations of that profound principle. It's happening above you every clear night, quietly teaching you something extraordinary. Now here's one last thought that I always find both humbling and comforting. Imagine you could somehow step outside the atmosphere, far away from Earth. You look back at the night sky. The stars are perfectly steady, no flicker, no shimmer. Just silent, unwavering points of light. That's what the universe looks like in its natural state, calm, stable, immense. The twinkling, the drama, the sparkling beauty we associate with stars is actually a product of our perspective from within a thin shell of moving air. In other words, the magic we see in the sky is partly created by our own environment. And that's a lovely metaphor for something much bigger, because so much of what we find beautiful, mysterious, or emotionally powerful about the world isn't just out there. It arises from the interaction between us and what we observe, between our position, our limitations, our viewpoint, and the reality beyond us. The stars themselves are steady, but from where we stand, they sparkle, and perhaps there's something deeply human about that. We don't experience the universe in its raw, silent form. We experience it through movement, distortion, and interpretation, through atmosphere, both literal and metaphorical. And that doesn't make our experience less real. If anything, it makes it richer. Because the twinkling reminds us that we are not outside the universe looking in. We are inside it, immersed in its processes, shaped by its mediums, participating in its unfolding. So the next time you see a star flicker, you can smile a little, because you'll know something most people don't stop to think about. You'll know that what you're seeing is not a restless star. It's a perfectly steady sun, shining calmly across unimaginable distances, and the tiny, invisible turbulence of your own planet gently stirring its light in the final moment before it reaches you. A quiet collaboration between the cosmos and the air above your head. A reminder that reality is always more subtle, more interconnected, and more beautiful than it first appears. And that even the smallest flicker in the night sky can tell a story that stretches across the entire universe.